Swayam Prabha. Digital India. Educated India.
So, today we are going to talk about geologic hazards related to subsidence and those related to expansive and collapsible soils. Okay. Now, let us look back first at the question set of the previous lesson. These are the questions. The first one, in the first question I asked you to list the typical impacts of mud flow. How far would the anticipated area of its influence is expected to extend from the location of the trigger? These are there are two parts to this question. So, the first part, to answer the first part, mud flow is really is a very fast landslide, and as a result typical impacts of mud flow could include damage to property, infrastructure, or even loss of life. Now, the second part, to answer the second part, mud flow essentially involves flow like behavior of soil material, and in this particular instance the soil that flows actually behaves like a viscous fluid, and it flows to a great distance from the location where the flow is triggered. So, you could easily expect the impact of mud flow to continue down gradient from the location where the slide is initiated to distances of a few kilometers. Second question was like this: why landslide inventory is an important factor in landslide hazard assessment. Now, the thought in this regard is like this, that if an area is prone to frequent occurrence of landslide, or there are very many instances of landslide in recent past in a given area, in that situation you would expect that similar unstable behavior to continue over the next few years in the near future. So, that is why if you get an area, you can ascribe a large number of landslides in a given area, then that area is likely to be more landslide prone than other areas where only a few landslides occur over a reasonable length of period in the past. Now, the third question that I asked was for you to explain the terms permanent factor map and grading ordinance. In permanent factor map, what you do basically is to actually prepare a map of relative hazard of landslide in regional scale, and in order to prepare that there are certain steps followed, and I am going to just quickly take an example in the next little bit to illustrate the steps involved there. But before that, let me finish up with the other questions. So, the next part of this third question was, what is grading ordinance? In grading ordinance, generally the local government passes a local local enforceable guideline involving limiting that actually limits the possibility of doing some excavation or steepen some slopes in a given area. So you cannot at your own will excavate or alter the geometry of a slope within the jurisdiction of the local government, which actually introduces such grading ordinances. However, this type of thought is quite rare in India, but I am sure that as more and more awareness comes into the technical community, the thought process is going to also get guided in these lines as it is in other developed countries. The fourth question, let me finish the fourth question before I give the example regarding the permanent factor map, preparation of permanent factor map. The fourth question again asks for the possible impacts of the, or cause rather, of which of the following actually. I gave you three possibilities: lowest flow, rock creep and solifluction. Asked you which one of the three would cause loss of life. Now, as was evident from what I discussed before, that for loss of life to occur, you need to have a very fast landslide in general. So out of these three processes, lowest flow is a very fast landslide process. On the other hand, rock creep and solifluction, they are very slow processes, so no loss of life is expected to occur as a result of rock creep or solifluction, whereas lowest flow could give rise to a large number of loss of life. Now let's get back to the steps which are involved in preparation of permanent factor map. So this is an example here. So you remember from the previous lesson that I was dealing with on this particular issue. You have to combine all the factors that affect landslide possibilities in a given area and express the quantities as fractions associated with different types of units that have different types of hazard possibilities. So the factors in this particular example are as shown in the first bullet there. These are all arranged in ascending order, and then what you do, you try several different classes. For example, if you have got a very small proportion of a given land unit affected by landslides or underlain by landslide debris, then we are going to call it class 1, and for that let's try the first. In the first trial, let's take the limits of permanent factors of 0.01 to 0.29 for that particular class. Class 2 is intermediate landslide hazard, and here the factors of the area that is affected by a landslide or underlain by landslide debris ranges between 0.29 and 0.58, and if you have got more than 0.58 percent of a given area underlain by landslide deposits or affected by landslide activities, then we are going to call it class 3. Now what we are going to do in the next step is to list all the factors that come in class 1, and those factors are shown in the third bullet there, and take the average of these quantities, and the average in this particular case is 0.07. Similarly, we calculate the averages for classes 2 and 3, and the averages for these two classes are respectively 0.46 and 0.745 for the example shown there. Then we calculate, actually there is something missing here, you should take a note of this one. We prepare sums of f1j minus the average of the factors in the first class. We take the square of the deviations and sum up the squares. So the squares are missing, so you have to really have a an exponent on the terms that appear within bracket. The exponent is 2 in this particular case, so you really take the sum of squares and then you sum up the whole thing, and what you get for the first class, for class 1, is a quantity 0.0534. Similarly, sum of squares of f2j minus f2 bar. F2 bar is the average of class 2. You find out all the deviations, take squares and sum it up for class 2, and you get a quantity of 0.0098, and similarly you get a quantity of 0.365 for class 3. Then we move on to the next step. Here what we do, we calculate we sum up all the 3 quantities that we obtained in the previous step like this, and we obtain a double summation. Here again the squares are missing, so you should note that there are squares in these terms which appear within bracket. So the result of this particular calculation of this step is 0.0996, and then what is done, we will try new interclass boundaries. If you recall, we had boundaries at 0.29 and 0.58 in this particular trial. We are going to try new interclass boundary and carry through the same steps again to compute the double sum result which we obtained in the previous step, and we try to see whether this number is going up or going down, and our objective is to minimize the quantity, the double summation quantity, the result of the double summation. And once we have obtained a minimum value, that is the interclass boundary that classifies the region into 3 zones of low, intermediate and high landslide hazard. And then a map is prepared showing the areas that come under the low hazard, intermediate hazard or high hazard. So that's how a permanent factor map is really prepared. That actually completes also the question set of the previous lesson, and now we move on with the subject matter of this particular lesson. So what we want to learn from this lesson, we would like to be able to identify subsidence hazard, then hazards due to swelling and collapsible soils, and list typical mitigation measures for each of these individual hazards. Okay, the first thing, there are 3 topics really, 3 subtopics: subsidence, expansive soil and collapsible soils, and we are going to take these 3 subtopics one by one. So first we consider the subsidence hazard, and let's first have a look at the causes, possible causes of subsidence. So if you have got any underground excavation, for that matter, underground opening, then that could be a cause of subsidence hazard, and an underground opening could be created as a result of underground mining activity such as longwall or room and pillar mining. Now what happens in a longwall mining, if you have got, for instance, if you have got an area underlain by economic minerals such as coal, what is done in longwall mining, a large area is gradually mined out, and the opening is allowed to collapse in a controlled manner. So longwall really allows the collapse of the roof of the mined out area, and as a result it also allows subsidence to develop, although in a controlled manner at the at the shallower depths, and the effect of this subsidence could in fact extend to the ground surface. Room and pillar mining, on the other hand, involves mining out the coal deposit or any other economic mineral by leaving out some pillars, and typically those pillars also include the economic mineral that is being mined out. So, room and pillar mining really is a little bit uneconomical, because it has to this particular process has to leave out some of the economic minerals. But anyway, because these pillars are left out, the opening, the mined out area it remains relatively stable over after the mining has been completed in a given area. But the problem here is, depending on the time of exposure and depending on weathering or depending on many other factors such as fire that spontaneously develop within mined out area of abandoned coal mines, some of the pillars that was left behind during the original mining activity could eventually fail, and because of this some subsidence could develop near the ground surface in a very fast and sometimes unpredictable manner. So, you really need to understand what is the difference between these two processes of mining, underground mining. One is longwall mining, another one is room and pillar mining. Whereas in longwall mining you allow the subsidence to develop, but that is done in a very controlled manner. So, the sequence could be engineered and the hazard because of the subsidence could be managed in the process. On the other hand, in case of room and pillar mining, the control is really not there that much. There could be other types of underground excavation which also leads to subsidence, such as if a tunnel is excavated within a few meters from the ground surface, that also could cause deformation, permanent deformation at the ground surface. Now, supported excavation other types can also cause slow and predictable subsidence, and because of the fact that here the deformation is quite slow and predictable, this could cause damage to the structures, but the loss of life in this particular case is minimal. In comparison, the behavior of subsidence features that develop because of room and pillar mining could be very fast in some instances, and it could be quite unpredictable. So, in that situation there could be property damage, and even in some instances there could be loss of life also because of that. Dissolution of some type of soluble rock such as limestone in karstic terrain could also lead to subsidence, and this type of subsidence often is fast, and timing and location of development of sinkhole because of dissolution of underground near surface soluble rock is quite difficult to predict. So, this also has the potential to lead to loss of life, as well as it could damage properties. Then dewatering is also another agent that causes subsidence, and we have discussed this particular aspect in some detail when we were talking about groundwater, and dewatering related subsidence is particularly significant in case of fine grained soils or aquitures. This type of damage is slow and predictable in general if the subsurface soils is properly characterized, and amount of dewatering that is going on in a given area can also be quantified. But in some areas near the location of dewatering activity properties could get damaged because of the relative displacement that could prevail across the particular structure in consideration. So, because of the fact that in this particular case, especially near the location where the dewatering is going on, there is a possibility of uneven settlement, uneven subsidence. The structures that are constructed near this particular location could be damaged because of the uneven settlement. You should realize that if the entire breadth of the area across the structure settles uniformly, then there is very little possibility of damage to the structure, especially if the subsidence occurs at a slow pace. Now, on the other hand, even if the subsidence occurs at a slow pace, there is an uneven settlement, uneven subsidence across the structure or across the building, then there could be a substantial damage caused because of the uneven settlement. So, these in a nutshell are the different types of agents that could cause subsidence, and what are the and their effects really about the nature of damage that could be caused because of these because of these individual agents of subsidence. Now, let us look at the features that could be caused by subsidence resulting from the causes that we discussed in the previous two slides. The first one that could develop, the first type of feature that could develop is called a hole, where you have got a relatively small area affected by subsidence, and in this particular case typically the deformation, the ground deformation develops quite fast, and because of the fact that the lateral extent of the ground deformation is quite narrow or quite focused within a small area. So, if there is any property within this particular area that is affected, the damage could be severe damage could be caused to those properties. Now, examples of holes are those that develop in areas underlain by shallow underground mining activity, typically room and pillar mining, and where very few mine pillars give way at a given time. So, that could cause, as we are going to see in the next little bit, that could cause a hole to develop within the ground. A hole could also develop because of groundwater erosion, in which groundwater carries soil fines into the cracks and crevices within rock underneath, or into the excavation that may be there within the rock because of the presence of a tunnel or cavity within the rock at a shallow depth. So, hole could develop because of groundwater erosion. Hole could also develop because of the dissolution activities related to groundwater, particularly if you have got soluble rocks present near the ground surface, and this type of holes that develops because of the dissolution of shallow soluble rock is called a sinkhole. And as I mentioned, hole could develop violently and in a very unpredictable manner. So, this could also cause loss of life in addition to property damage. The second type of subsidence feature that we are going to consider here is called sags or troughs. and in this particular case the subsidence develops over area which has got a wide horizontal extent, typically in comparison with the subsidence feature, with the previous subsidence feature, that is hole or a sinkhole. And sags typically develop as a result of collapse of the roof of an underground mine opening or underground excavation over a large aerial extent. Room and pillar mining often is a cause of the development of sags or trough. This type of subsidence typically develops relatively slowly, and as a result the property damage is relatively minor in this particular case in comparison with the other subsidence feature, as well as loss of life is the chance of loss of life in this particular case is also minimal. Sags or troughs could also develop when the roof of an underground mined out area collapses over a large aerial extent because of near simultaneous failure of a large number of pillar in case of room and pillar mining as well. So that is that you should also remember. So they could sags or trough could develop because of long wall mining, as well as because in some instances in areas in areas underlain by room and pillar, abandoned room and pillar mines as well, if a number of pillars give way at the same time. All right. Now this particular cartoon actually shows how a hole could develop. What is shown here is this. This one is the pillar, as we explained a little bit earlier, and these are the openings. This is the opening which is already mined out, and in this instance this one is another opening, another mined out opening, and another pillar is out here. So in this instance what happened, the roof or in this particular area collapsed. So roof here collapsed, and that collapse of the roof of mined out opening this collapse actually led to the dumping of debris. So this one is the debris that got generated because of the roof collapse, and in the process a hole formed in this particular area. Now you can easily imagine, if this particular building that is shown here was to be nearer to the hole, then the building would have had to undergo severe damage. Now there is a little bit of roof collapse out for this particular opening as well, but the collapse is yet to daylight near surface, and eventually there is a possibility of development of another hole in this particular area in this instance, and you really do not know, it is difficult to predict how long it is going to require for before a hole develops in this particular area. But what we can say that the area the area shown in this particular cross section is in general susceptible to development of subsidence holes. Okay. Now let us look at the other type of subsidence feature, which is a trough, and you can see in this particular case simultaneous collapse of several different openings is the cause for the development of this type of feature, and as a result what you can see is development of subsidence over a relatively wide area. Often what happens, you have got cracks appearing at the boundary of the area that is likely to undergo subsidence of this type, and these cracks appear before the actual subsidence occur. So the presence or appearance of cracks could be taken as a precursor to the development of this type of subsidence feature. Now another thing I want you to notice, that this particular structure is within the zone affected by the subsidence, but since away from the margins of the trough, the relative settlement or the differential settlement is typically small. As a result, the possibility of property damage is rather small if the property is located away from the margin of the subsidence feature, although even if the property falls within the affected area. Now long and pillar mining allows this type of feature to develop in a very controlled manner, and it could actually sequence the mining the engineers could sequence their mining activity in such a manner that the areas, inhabited areas, they could be spared from this type of damage. All right. So subsidence vulnerability, then how do you actually assess subsidence vulnerability, and that to a large extent it follows from the discussion that we already had regarding subsidence. Areas underlain by shallow room and pillar mine workings, they are particularly vulnerable to subsidence, and there are instances of this type of subsidence in eastern India, in the coal fields of Raniganj in western West Bengal and Jharia in the adjoining Jharkhand area. That area is affected by subsidence because of shallow underground room and pillar mining. And what complicated the matter in many of these areas is because of the burning of the coal that is left behind from previous mining activities, and these burning is causing mine pillars that were left behind to collapse, and some areas they are sinking in the Raniganj and Jharia coalfield area in a very unpredictable and disturbing manner. Now areas underlain by soluble bedrock or erodible deposits at shallow depths, they are also vulnerable to subsidence. Vulnerable to subsidence. Examples in the Indian context include Rewa in Raipur, where soluble rock is found within a shallow depth from the ground surface, and sinkholes develop quite frequently in those areas. Gulbarga district in Karnataka, and in fact in many other areas of Karnataka in southern India, is also affected by erosion related subsidence features that we discussed a little bit earlier. Now subsidence vulnerability is generally considered to be present in areas which has a history of frequent subsidence in near past, as we have discussed earlier. Now, what are the mitigation strategies to account for to counteract the effects of subsidence? You can identify the areas where there are underground cavities. The cavities could be man-made, or they could be solution channels or caves, caverns, because of groundwater movement through soluble bedrock. Then you could try to predict the development of subsidence, as is a strategy in case of longwall mining. You could avoid or evacuate hazardous areas. Then there could be structural measures, which include backfilling or grouting of underground caverns and cavities or mined out areas. Then you could include some measures which can absorb compression, such as perimeter trench. I am just going to explain it in the next little bit. Just bear with me for a second. You could also have a structural design so that the building is capable of absorbing a relatively large amount of differential settlement, but this measure could be quite expensive actually, and this could make residential development in the area unviable. Then you could have flexible utility connections connecting the building to connecting into a residential building or commercial properties, such as sewer lines or gas connection or telephone cables. So these are the measures typically included in areas affected by subsidence. But let me explain what I meant by perimeter trench option, which I considered here. Okay, let me open up a page here. So let's say you have got an area that you expect is going to be affected by a subsidence of this nature, and you expect that the structure is out here. So you can imagine that the soil layers, because of the development of this type of feature, the soil in this area is compressed towards the structure, and that causes many structural failures. So what is done in these instances, if you could dig a trench and backfill the trench with soft compressible material such as loosely spaced sand or other clay filling, other soil filling. These are the perimeter trenches, and we backfill, as I mentioned, backfill the trench with compressible filling such as loose sand. Then that to a large degree controls the damage that could be caused to a structure within the zone of subsidence, because the compressible backfill within the perimeter trench is going to accommodate the amount of compression that is observed within the area affected by subsidence. So this is the area in this particular case affected by subsidence. Okay, so that is the function of perimeter trench. Okay, now next topic is really shrinking and swelling soils. Now, what kind of geological setting readily gets associated with shrinking and swelling soils, they are as follows: smectite minerals and sometimes illite minerals. If there is an abundance of smectite and illite clays, then that is an area you should watch out for as far as swelling and shrinking is concerned. Then weathered rock containing clay minerals, that is also susceptible to swelling and shrinking, because weathering of many types of rocks that leads to the development of clay minerals actually leads to an expansion in the volume of the material. So that leads to swelling. Examples of typical geologic settings affected by shrinking and swelling are as follows: clay shale, clay siltstone, sandstone, and black cotton soil. Now let's look at very quickly the mechanism that leads to the development of shrinking and swelling. For clays, what happens? There is a volume change triggered by entry and exit of water in between the plate-like particles that we talked about some time back in this course. And for weathered rock, volume change is initiated because of the chemical change or chemical weathering of the rock forming minerals, and particularly as the rock minerals, they get weathered and lead to the formation of different types of clay minerals, there is a volumetric expansion associated with that type of activity. So that is the reason why if there is an abundance of clay minerals, particularly smectitic and illitic minerals, then that area you can expect a lot of swelling and damages related to swelling and shrinking. Okay. Now this is an example of consequence of shrinking and swelling. Typically the process is quite slow in many situations because it requires entry and exit of water into the matrix of fine grained clay particles. So the process generally occurs at a slow pace, and this in fact could lead to a severe damage of property, but usually loss of life, the possibility of loss of life could be discounted. Now on the right I show a picture of an office complex in southwestern West Bengal, which is underlain by swelling soil, and here you can see that the portion of the building towards the left it has separated out from the portion of the building which is towards the right of this particular picture. And what is happening here is that the soil is pushing in this direction, and that is pushing the that is actually splitting the building into two different parts in this particular case. And this crack here is approximately 200 to 250 millimeter in this particular case. So this entire thing is occurring because of the presence of swelling clay underneath this particular structure. Now you should realize that this swelling clay is not categorized. Actually that was one of the sites that we investigated. This particular swelling clay is not categorized as high swelling clay. In fact the swell potential is medium to low in this particular instance, but even then you can see that quite a significant property damage has been initiated because of the swelling activity of the underlying soil layer. You have to identify shrinking and swelling is largely accounted for by identifying the hazard and accounting for the possibility of shrinking and swelling. So hazard identification is typically involved typically involves identification of mineralogy and clay content, usually greater the clay mineral percentage, plasticity index and stiffness, greater is the swell potential. Usually soils affected by swelling exhibit an appearance of popcorn. Actually, if you look at the surface of the soil, shrinking and swelling soil, natural surface of shrinking and swelling soil, they often take the appearance of popcorn, just like you can imagine the surface, it looks like the surface of a cauliflower. Then we need to assess the engineering behavior of the soils that are likely to be affected by shrinking and swelling, and there are many correlations that are available which could allows the engineer to estimate the pressure that could come, that the structure to be constructed on swelling clay because of shrinking and swelling, because of water ingress and egress from the mineralogy and from Atterberg limits. We are going to look at how do we actually quantify the shrinking or classify or identify the shrinking and swelling tendency from Atterberg limits of the soils, and that is shown in this particular table here. And what you can see here is generally high shrinking and swelling is associated with soils which has got liquid limit of greater than 60%. You should look back at your notes, previous notes, to check out what is meant by liquid limit. And plasticity index of the soil that are characterized as high swelling, high swelling and shrinking, high swell and shrinkage potential. Typical plasticity index ranges above 35%, and when you have got very low liquid limit, typically smaller than 35%, or small plasticity index, typically smaller than 12%, then it is typically assumed that there is no swell potential, shrink swell potential. And there are two more classes in between. One is medium shrink swell potential, and another one is low shrink swell potential, as shown in this particular table. Now, you need, if you identify, if you ascribe some swell potential, shrink swell potential to the soil at a given location, then you have to do laboratory testing of the material, bring sample of the soil to the laboratory and do some testing in order to quantify how much of swell pressure that could be associated with the deposit, or how much of pressure a structure is going to encounter because of entry and egress of water into the soil underneath the structure. So, once that can be ascertained, then special structural design can be done to accommodate the amount of movement, or it could require some ground modification in order to minimize the entry and egress of water that is the prime that causes the swelling or shrinking in the first place. Okay. So, that actually leads us to the mitigation, typical mitigation strategies associated with shrinking and swelling. First, as usual, as we have seen over and over again, the first mitigation strategy is to avoid the areas which are affected by shrinking and swelling, but that is not always possible. So, we have to move on to the other mitigation measures. We could remove the problem soil within the zone of moisture change, or the zone which is affected by entry and egress of water, which is typically within the top 3 to 5 meters from ground surface. Then you could control moisture ingress and egress by drainage control underneath the structure, or control over development of lawns or development of plantation within a close proximity of a particular structure. You could also go for chemical stabilization, mixing up the soil with lime or fly ash typically, and that minimizes the tendency of shrinkage and swelling to a great extent. The final topic that we are going to look at in this case is that associated with collapsible soils. Collapsible soils are those soils that collapse without any additional loading because of wetting. When water gets entry into the soil, the structure collapses. This type of soil is often found in arid or semi-arid climates. Typically, the soils that have weak interparticle bonds, such as those because of deposition of salt or calcium carbonate deposits at the grain contact, they get classified as collapsible soil. Mechanism that leads to collapse is as follows. Soil structure collapses when entry of water dissolves the weak cementation bond that causes the collapse. As we did for shrinking and swelling soils and rocks, we are going to try to identify the hazard associated with collapsible soil. Collapsible soils typically occur in climates other than could occur in climates other than arid or semi-arid, but they are more in abundance in areas that are arid or semi-arid. The collapsible soils are typically dry. They are usually light colored, and they have got liquid limit typically below 45%, plasticity index typically below 25%, and the void ratio is typically above 0.7. Mitigation strategies associated in order to avoid problems associated with collapsible soils. If collapsible soil is encountered at shallow depth, then the soil it is imperative that the soil is not allowed to get wet, or pre-wetting before any structure or facility is constructed, followed by heavy compaction of the soil before the construction of the structure or building or road or other facilities. If collapsible soil occurs at great depth, then what could be done is to go for deep foundation that transfers the load of the structure to a layer underneath the soil that may be affected by collapse because of entry of water. In this case also we could go for chemical stabilization, and that typical procedures involve treatment of the soil with sodium silicate and or calcium chloride solution, which reinforces the weak cementation bond and gives some permanence to the strength of the interparticle bond. Alternatively, we could also go for jet grouting that involves pumping of grout material, cementitious or other grout material at great pressure to actually reinforce the interparticle bond, as well as to compact the soil and compact the potentially collapsible soil. So these are the typical mitigation strategies that one often uses for collapsible soils. So now we have come to the end of this particular lesson. we summarize this lesson, what we learned here. We looked at a list of the features associated with subsidence and how the features develop, nature of subsidence hazard and mitigation strategy, identification of hazard related to swelling and collapsible soils, and we also looked at the mitigation strategies to account for the hazards related to swelling and collapsible soils. We end this lesson with a question set. The first question that I ask is whether the following statements are true or false. The first statement is swelling soils are found only in desert. Second one is collapsible soils are usually dry. Second question, can a clay silt soil of high plasticity be typically classified as collapsible soil? Third one, can a soil with high swell potential be classified as CH? You should look back to your earlier notes in this particular course to answer these questions. Fourth question that I asked was explain the following sinkhole and trough, and finally list the typical mitigation measures against subsidence hazard. Okay, so that brings us to the end of this lesson. Try to answer the questions that I gave at your leisure. I am going to give you the answer to this question when we meet with the next lesson. So until then, bye for now. Thank you.
Hello everyone, and welcome back. We are going to get into the first laboratory session of this course today, and we are going to talk about preparation of geologic sections from geologic maps in this particular laboratory. We have already looked at the salient features of geologic maps and geologic sections earlier in one of the theoretical lessons. Today we are going to have a practical demonstration on this business of preparation of geologic sections. I will also take this opportunity of wrapping up the question set of the previous lesson before we begin with the preparation of geologic sections. This is the question set of the previous lesson. The first question that was asked was whether the following statements are true or false. The first statement was swelling soils are found only in desert. This is more often than not is true. However, swelling soils are also found in non-desert environment, particularly in fine-grained soils where there is a lot of smectite minerals present. Swelling soils could also be present in situations where there are a lot of clay minerals between rock joints. In such situations also there could be a lot of potential for swelling in the shallow layers near the ground surface. And these settings, these geologic settings, are not necessarily found in desert. They are also found in other hydrometeorologic environments.